quick recap. I did so much yesterday, I thought, hold on, I had better do at least this. Like a little recap before I jump into anything else. Let's call this recap. And all you see on, let's say, the quiz next Wednesday or the exam coming up on Friday, you see something like this. Something like that. The absolute value of 4x subtract 1 is less than 7. Now tell me, based on what we did yesterday, what would be a nice approach to take on this? I'll tell you one of those two rules. You gotta know your rules. So can someone translate right quickly for me? Because when you get to a calc class, they're going to assume that you know how to translate that right quickly and drop the absolute value bars. Just drop the bars with the help of the rule there. Anyone remind me what this really says without the absolute value bars? And then we'll solve. What does this mean?
This means that -7
Yeah.
is, so it will be less than.
That's that.
Less than 4x minus 1, and then that is less than 7.
And that's mathematics. But there it is. The bars are gone. That's what the rule says. And I can solve it. I can solve for x. Easily add 1. All 3 parts. Got it. I'm gonna end up with what? -6. Less than looks like 4x. You drop out. Looks like less than 8. Divided by 4. No problem. Of course, this reduces down to a -3/2. I guess this is a 2, if I had no mistake. So there's the answer. That's all you have to do. Now, the answer might be asked to be expressed in interval notation. There's no problem here. This says you're going from a -3/2 up to a 2. And you're finished. If I made no mistake in the arithmetic. Done. Okay. Letter B, which is more recap. All that we did yesterday. Marina, I know your notes you sent out, that helps. That really helps. The next one, guys, looks like this. Absolute value of 3x plus 4 is greater than or equal to 5. First thing you're thinking, well, I've got to drop those absolute value bars. But you can't drop them until you realize which rule there will help me to drop them. Guys who has an idea, be careful, this might be the longer one, but I need a rule to follow. The second rule, there's only 2 rules here right now. I need to apply the second rule here.
It's less than negative.
Let me again.
I don't know how to word it other than it's less than or equal to -5. I don't know the rule.
Hang on. I'll give you a hint. This is the one that requires 2 parts.
Yes.
There are 2 parts to this rule. This one, I love this one, it's just a single statement you made on the first one. This one, those one require 2 parts. Someone give me at least 1 part. Yes?
3x plus 4 is greater than or equal to 5.
Okay, now 3x plus 4 is greater than or equal to 5. And I guess a or here. And what's the other one?
3x plus 4 is less than or equal to -5.
3x plus 4 is less than or equal to a -5. You guys agree? Now, I'm trying to remember standing here how I stated when I did it. The rule here. Guys, I think I had an absolute value of, I think your textbook uses a u. If the absolute value of u is greater than, I think they use an a. I think that's the way I presented it to you in your notes. Does anyone remember exactly what that looked like from, I think it's from your textbook. Just this right here, which is the rule here. Yes?
If the absolute value of u is greater than a, then u is less than -a,
U is less than -a,
or u is greater than a.
or U is greater than A. Okay? And my student just gave me, U is less than -a. U in this case is all this, inside here is U. 3x plus plus four. 3x plus four is less than negative a in my case is five. I'll match things up. So she gave this to me, which looks good. And the other one says consider u is greater than a, or equal to in this case. And of course, that is 3x plus 4 is greater or equal to 5, and she gave that to me there. You guys agree? Did I split it up correctly with the rule? If you solve each one of these, I see students still looking at this one. This one's a little strange. This, I love this one. But when it says greater than, be careful, there's two parts here to be considered. Did we have the two parts correctly written down? Yes? No? Okay, let's solve each one, guys. If I solve the first one here, I'm just right on the top here. I think we're going to end up with x is greater than or equal to, help me out. I'm going to move that 4 over, subtract it, divide by 3. What is that? 1/3? That was done then. This one, if I solve for x, move the 4 over, I guess it's a -9, divide by 3. What is that? -3? I didn't click it. Is that true? It's real. Quickly. Now, those are the intervals on which the solution lies. Now, I should express this in interval notation. Guys, we all know this means, you want to take this one first, x is greater than or equal to 1/3 means what? Bracket. 1/3 through infinity. And this one means what? In terms of an interval, is that negative infinity up to, what was it, -3 here? Bracket, yes or no, guys? Is that true? And we'll take both those to express the solution. Okay, so we got this, I'm going to put it over here. A negative infinity up to a -3, was it? Yes, bracket. Did we use the union symbol yesterday? I think we did, didn't we? And 1/3 to infinity. That's it. Finish. You gotta know this. That calc instructor's not gonna have the patience. They're teaching calculus. They're gonna move on to something. I guess I didn't get past this right here. You gotta get past this first in that calc course and move on. And one more little item here I thought about before I jump into that chapter 3, and a lot of chapter 3 done tonight, was this on inequalities. Yes, absolute value, x subtract 1 is greater than 0. Now you know how life is. Things happen consistently for a while, then all of a sudden something happens that does not right fall into place. I don't know if you want to attempt one of the two rules there, we could. Or it might be one of those where you just look at it and say, Professor, I think I see what's going on, it's just the way it looks. I'm not going to tell from my knowledge of what an absolute value does. I think I might see what the answer is right now, without applying a rule. And sometimes that happens. Does anyone see what's happening? Or does anyone see the answer? Jonathan, go for it.
All numbers?
Okay, now all real numbers. Now he says that I can replace x by all real numbers. Now I'll tell you this much, you're so close. By the way, guys, if I pick the absolute value, no matter what's inside there, we'll always get a positive answer. Except what?
1.
Except 1. I can't put a 1 in there. Why? Yeah, that would give me a 0, and I did not put the equals box here so you could include 0. Okay, and that in interval notation, just by mere observation, is negative infinity up to, what was it, 1 union 1/3 infinity. I can use anything but 1. And sometimes that happens. Okay, a little recap here, guys. Please do as well in that exam as I saw those quiz scores. That's what I want. I was telling another colleague of mine how happy I was with those scores last night. He wasn't too happy with his, but I was happy with mine. Okay, guys, moving to part 2. Now, I know my students by now, most of my students. most of my students are moving on. They're saying, Professor, I'm moving on. If that syllabus says I'm in chapter 3 and I see the homework assignment and the pages, I'm gonna try some. And see if I can work these out. Guys, I'm gonna do a lot in chapter 3. And to lead into it, and I got some handouts here, it's gonna help us, and also lead into your extra credit. Part 2 is all about, or chapter 3 is all about this. A polynomial function. And I think I mentioned yesterday, right at the end of class, that this polynomial, many names translated, yes, we've seen somewhere in our math courses, this monomial, which has only one term, contains one term, monomial. If it contains two terms, I'm trying to find a better marker here, two terms, we're into a binomial, three terms, try to do it again, trinomial, so let's go ahead into the binomial. You know what that looks like, and let's put an example right quick, guys, on the side here. X squared plus 4 consists of two terms, that's a binomial. At the same time, they call all these polynomials. Monomial, let's make up one here right quickly, 3x squared y to the 4th. Just one term. That's thought as monomial. Number 3, the other that you may have worked with before is a trinomial. 3 terms. So this is more what we have been working with in this class, like something like that. That's 3 terms. Trinomial. Okay? And you list others. Now, are there 4 terms? Of course there are. 5 terms? Of course there are. Your extra credit today, I think, has 7. I think it has 8 terms. And your extra credit's going to involve you doing something to it. And that's something I'll tell you ahead of time. If I ask you to solve this one, find the zeros of this trinomial, you say, Professor, that's a quadratic. Yeah, but at the same time, it's a trinomial. That's 3 terms. What would you do if you were asked to find the zeros of that quadratic trinomial? You say, well, I'll either try to factor or use quadratic formula. That's beautiful. But wait till you see one with 8 terms. And it may start out with an x to the 8th. I've never shown you one of those. So you're not going to use quadratic formula. That's not a quadratic. You can't use quadratic formula. So we got to come up with a plan on how to find those zeros and how to solve and get those zeros. Okay, guys? We jump into, those are the special terms there. We go into part B. I really want to go here. Let me list 3 polynomial functions that are unique for a reason here. Let me do this. Beautiful, beautiful, beautiful. First, p of x is equal to, I am going to do this. I wrote myself a note for a reason. I am going to do a quadratic first. 2x squared plus 3x minus 2. For a reason. Before I jump into the heavy stuff. That's a trinomial, quadratic. I would like to, with your help, because you're going to have one of these on the, maybe the quiz, for sure, the exam. I'd like, with your help, markers will show up here well. I'd like to graph that. I'd like to make a sketch of that trinomial. And should, in this case, sketch into what, a parabola? So look for a sketch of a parabola. Guys? Parabola, I first will ask you to place this in something called, and you've seen this before, something called vertex form. In other words, you're going to rewrite this function, quadratic, in vertex form. And I think you recall to do that, you have to use a process called completion of the square. Now, I may approach the completion of the square a little differently than adding, rather than add those blanks on each side like we usually do, you can do that. It's a little quicker here. Let me see what, I need a good marker here. Okay, let's write this guy as y is equal to 2x squared plus 3x subtract 2. Still such a good marker would be a little bit here. Now, can anyone tell me, please, if I will put it in what is known as vertex form, let me jot down what the vertex form is meant to look like. We know what it is, but just in case. The vertex form. I'm looking for y is equal to, much better, a times x subtract h squared plus k. If I can place it in that form, I sort of know something about it. And what is that something that may help me later on to graph it fairly quickly? What is that something that I will know if I can take this and put it in that so-called vertex form, which your textbook, I think, writes like this. What do we know about this if it's in that form? You should know where the vertex is. And right now, in this form, the vertex would be labeled as, it's a horizontal shift to the right, what, h? So we have an h for sure. And on the end, we all know about transformations, this k represents what? A vertical shift up to k, or down k, wherever k is. So the vertex is merely hk. And then from there, I can sort of play with it and sketch it. Now, let's go back. I need to place this right here in, this in this form here. And I do it by completion of the square. Place it in vertex form. Now, someone in this class tell me, since this is a little recap here, what might you suggest I do first, that we always do, if they ask us to complete the square? Yes?
Factor up the 2.
The 2 has to go. Now, I'm gonna do this, rather than dividing both sides by 2, which you could do, I'm gonna just factor out a 2, 8 nothing, that's what you want to do, just factor. So let's take out a 2, watch the math here. Okay, at this point, I take 2 out. And make sure I did take the 2 out, factor out 2 out correctly. Do I have the x's in there to themselves? Is that true? Inside the parenthesis right now, the x terms are to themselves inside there. Those are the ones we want to complete the square on. So why not put the blank already here if we need to show that's what you need to complete the square of those x's. But don't forget, I think on the end here, was there a minus 2? It's still there. Let's isolate the x's. Watch carefully. It's a little shorter version of how to complete the square. What's required from that blank? We're going to take 1/2 or 3/2, which is, I hope, what, 3/4? Is it? And then square it is how much? 9/16. Seems like I see that come up so much. Now guys, you say, well, Professor, I see that's 9/16, and I know how to find that. Now the value that you actually have though is, since this 2 stuck out front, it's 2 times. That's the value of 9/16, which I think becomes what? 9/8. Was there a 9/8 back in my original? I didn't have a 9/8 back in the original, did I? So you got to keep in mind, I really still have to keep the original. Well, the original had a 9/8. So what I can do right quickly to show, hold on, Professor, just go ahead and subtract that value out, and it's gone. I realize you got 2 times this, that's 9/8. Now subtract 9/8, they drop out, they're gone, and you're back to the original. I'm just rewriting the original. And guys, let me check real quick and make sure it is the original here. If I use the distributive property at 2 times that, yes, I get that. 2 times this, guys, is 3x. I get that. Beautiful. 2 times this is 9/8, which we put here to cancel. It's gone. And what does it leave on the end? -2. Does everything match up? Same one. Okay. So now this should factor. What's your way to complete the square and do your work here? Y is equal to, this becomes 2. I guess this is x plus 3/4 squared. Now all this business, common denominator of 8, I think it's a -25/8. Check my true? Well, of course it is. Now, what's the benefit of changing this beautiful quadratic, which contains no fractions up here? Looks so nice, nice whole numbers. And all of a sudden you say, Professor, why change that into this awkward looking thing that has fractions? I have to find the vertex. Now, where's my turning point? My turning point, the vertex will be, this is meant to be a horizontal shift to the left. You can think of it like that as, to the left would be what? -3/4. And a vertical shift down, which like this, 25/8. These numbers tell me this. That's my turning point. Okay, guys? Now, I could finish it up. I could plot that and sketch and find the x-intercept, the y-intercept, and see what this sketch looks like. That's all a recap. Are we okay with this right now? Could we finish it up and actually sketch it ourselves? I did the hard part for you. I found the vertex. Could we actually finish it up ourselves for an exam question? Or should I finish this one up? Someone give me some input. But that's all recap. I think we've done something like this before. I think we have, haven't we? I think we have. Okay, so we'll stop there. I'm going to sketch that. Should be a parabola, something we've done before, but I did the hard part for you. Now, letter C. Now, I like to look at this. I'm going to call this P of X. Another polynomial function. And this one is not quadratic. If I get my planning correctly here. Okay, hang on. Oh, this one's huge. Oh, this one's 2P. Okay, here goes. P of X is equal to, yes, X cubed. Subtract 2x squared minus 3x. I can look at it and make sure everything's good. Looks good. Now, should I jump in and try to complete the square on it also, like I did here, and maybe find something and sketch it? Can I do that here? No, it's not a quadratic. It's a cubic. I think also my next one's a quartic, next to the fourth. Okay, now I'm going to actually graph this one. You have not in my class seen the sketch of one like this. We've all seen a sketch of a parabola, but you have not seen this. Now guys, what am I going to do to deal with this? We got options here. Miriam, you were asking about this. I, as a student, I think you would look at this and say, well, Professor, I see a common factor. That might help take out a common factor of x, which might help you to get to where you want to go. And let's see. Take out that x, much better. X squared minus 2x minus 3. If I think I take a closer look, I think it factors further into P of x is equal to x, and I think it factors into x subtract 3, x plus 1. Check my factoring out, guys. I'm going to block this off. Please tell me, is that what you see? At least I see that for this cubic. Then one thing that might help us on the side, and I'll ask this now, can anyone look at this and tell me, when I get to the grid, which I have not done yet, where are the x-intercepts? Where are you guaranteed that this, whatever the graph looks like, it's not going to be a parabola, it's not going to be a circle, it's not going to be a straight line. Anyone tell me where the x-intercepts would be just by merely looking at that?
0, 3, and -1.
There, I got you. You split those up, set each one equal to 0, and you'll find, like we do when we actually find zeros, we'll find these quickly to be x is equal to 0, x is equal to 3, x is equal to a -1, and I'm going to write these like this for today. I'm going to write these as ordered pairs to show these are my x-intercepts. I'm going to go to the grid with that much and say, well, Professor, at least to get some partial credits, if you ask me to graph this thing, I could at least do do this on the grid, we'll try that. Plot those points, 0, 0, out 3, 0. Right here, and -1, 0. Stepping back and looking at it, you say, well, just connect those three, Professor. Get a nice straight line, connect those 3 points, and turn my paper in, I'm finished. This course is so easy. You know, all my friends take this course. Just connect the 3 points. You know you can't do that. This is not a straight line, this is not linear. Now, can anyone tell me what you think might be good that we've done in this class to do to approach next in an attempt to see what this graph looks like? And I know the graph's gonna pick up those 3 points. Who has an idea? Oh, I think I heard someone say something. Something we've done in this class. Not from the textbook, I don't think the textbook approaches the way I'm gonna approach this first. Who has an idea? Yes?
Find 1%.
Do it again.
Find 1%.
Okay, now, we looked out here, I think the y-intercept is also gonna be 0. Is it, guys? I think the y-intercept, you go through and replace all those x's by 0, calculate, I think, I had the x and y-intercept both to be 0 there. We got that out of the way. Now something else to get, those points connect, they gotta connect. The graph has to connect them. But it's not gonna be a parabola, because it's not a quadratic, it's a cubic. Yes?
Make a table.
I can make a table, always.
Like
Try points, plug in points. Something else that we've done in this class that finally comes into play here. Sign analysis. You can quickly go on the side there, and you have had that in mind. Sign analysis, just go on the side here. Say, Professor, I will do this then. On the side here, draw the number line, take my points I'm interested in, -1, 0, and out to 3. Those are like my critical numbers in the sign analysis. And then start testing with a number of your choice. We know how to do sign analysis. And you guys out to the left of -1, here I am. I'm patient here today. -2, we'll try. In between these two, we'll try -1/2. If you guys can see this color here. Out between 0 and 3, we'll try 1. Don't you mess up here, guys. And out to the right, we'll try 4. And we'll just patiently put those numbers in. If I put -2 in, my test number, where am I gonna put it? Right here. Replace all these x's by -2. So we end up with this looking like this. A negative out front, then -2 subtract 3, that's a -5. Another negative. -2 plus 1 gives me another negative. Don't we mess up. Is that true? Is that altogether negative? Well, of course it is. Now what might that tell me is going on out here to the left of -1? The only thing it's telling me, since I got a negative result by sign analysis, what does that tell me about the graph out there to the left? Where's its location? Where's it located? It's below the x-axis. That's what the negative sign indicates. It's below the x-axis. So just a quick shape, you'll say, Professor, what do you mean? You just place it below. But like what though? Well, it's not a straight line. So if I see something like this, like maybe a curve, as long as it's below, I'm good. It's all below, out to the left of -1. Now here we go, we're going to start testing now, or we are going to test in between. My test number is -1/2. What's happening in between? Let's try -1/2. Replace x by -1/2, of course it's negative. Just leave that in the red. -1/2 subtract 3, negative. A negative 1/2 plus 1, positive. I hope I did that correctly. All that together is positive. So that tells me where is my graph located between -1 and 0. It's above the x-axis. It's positive. I gotta erase this, so put the graph above. That was my test. After I do that, yes, it's gonna be above. And how far above it goes, I don't know, but it's gotta come back and pick up 0. I don't know how far above unless I test the number. Aiden, between 0 and 3, who knows, it may stay above. I'm testing 1. If I put a 1 in there, 1 for sign analysis, that's positive. 1 subtract 3, negative. 1 plus 1, positive. Is it true?
Yep.
I think all that together is what, negative?
Negative,
So that tells me now it falls back to low. And how far down does it drop? I don't know, you don't know, until we test a point, another point, somewhere else. Right now though, all I'm interested in, it goes down, it's gotta come back up though, and pick up that 3. That's the next intercept. Out to the right of 3, I'm trying a 4. Guys, I think 4 makes all those positive out here. And since they're all positive, it says out here to the right of 3, my graph should be where? Back above the x-axis. Is that true? That's an application of sign analysis. Just testing to see whether it's going to be above or below. Jonathan, the only issue is, I do not know, unless I form a table for you guys on the quiz or the exam, I don't know exactly how high this might go. Who knows? I didn't test and find the exact location. It may be way up here. Who knows? I don't know. At this point right here, maybe way down here. We don't know. Sometimes we don't care, as long as you have the shape. You guys agree with the shape? There's a powerful way to use sign analysis. Now, let's connect something else since I have the graph in front of me. As I look at that graph from that last exam I gave, as I look at this graph, does this graph have any, what you would call a local max or a local min? Do you think on this graph, might there be a local max or a local min? Is there a local max, no matter how high it goes up, is there a local max in there somewhere? Definitely. I don't know where it is. You don't know where it is. Is there a point that you might identify as a local min on this graph? Looks like it's in here somewhere. This is a local minimum value down there. Is there an absolute max? Is there a point on this graph that's higher than everything? No, because I think this thing goes on forever, doesn't it? Is there an absolute min? A point that's lower than everything else? No. So we've got local max, local min. Mr. Park, Arena, trying to get these guys ready for calculus. Will you be able to, Mr. Park, Arena, mathematicians over there, will you be able to, about when they enter the doors of Math 7, will they be able to find exactly where these are? That's what Mr. Park shaking his head, yes.
Yeah.
Arena?
Yes.
They'll be able to find. And how will they do that when they reach Math 7?
By derivative
Give me a
critical,
second again.
by finding critical numbers through
Okay,
derivative.
something else. I need a key word. A
Derivative.
derivative. Which we're not doing here. So I'm going to ask you to find the exact location of that max and that min. They're going to do a Math 7, they're going to say, don't stop there, pick up where Ramsey left off, now find exactly what is that local max, not local min. That's where the calculus comes in. Is there an interval on which this red graph is increasing? Is it increasing somewhere? Now, I don't have numbers to work with, but is it rising from left to right? Is this thing rising like this from negative infinity up to whatever that number is? Is that increasing? Of course, we talked about this earlier, had some on the last exam. Is there a decrease? Yes, if it drops down like this, there's a decrease. And then is there another increase over on the right there? Of course there is. If I place numbers there, you could actually label those with numbers, okay? So guys, who knows how this math all connects? You had, I think I asked you about local max, local min on the last exam. Now here we're coming back into it again. But there it is. Now, what I want to do though, here we go. We did through sign analysis, which I love. I want to draw another, if I can squeeze this in. Yeah, why not? That's a good way to do this. We did through sign analysis. And then go back over. Here we go. Please help me out here. On this, we said the x-intercept for these, I've already have those marked. We said through sign analysis on the side here that the graph looks something like this. That, up, goes back down, drops down, comes back up, picks up 3, and continues on its way. Is that basically what we're saying is happening based on this? So that's a graph. Is that true, guys? The basic shape of the graph I'm after. Taking into consideration sign analysis on the side here. Now, increasing, decreasing, you get easy as with that. I had some numbers there. What was I going to ask you? Something really nice here. What was it? Yes. First domain. From left to right, no problem. No problem on this one. Range. The up and down, no problem. Now, I would like to, for a reason, beautiful reason here, I'd like to add another graph, one of the basic graphs, to this grid. We have the graph. We have a rough sketch of what that graph of that function looks like. I'd like to add, for a reason, this graph on the same grid. Does everyone remember which parent graph, which basic graph that graph represents?
X cubed.
X cubed. Now, does my x cubed graph and my blue graph, does anyone see any similarities there at all? Yes, go ahead. Okay, please tell me, the blue graph drops down forever? Does my red graph do the same thing? Are these two behaving the same way? Only on the ends. Over here on this end, look at this, are these two behaving the same way? Are they rising? So out on the end, they call this end behavior. My blue graph is behaving just like the x cubed graph. Now, why I place the x cubed graph, Ramsey? Why not place x squared graph on this in the red? How did you know to place the x cubed and see a similarity between your graph and the x cubed graph? Why place x cubed? Jonathan?
Odd. Because it's an odd.
Well, it's something else.
And power of 3.
Yeah, I've got power of 3. I just x cubed. But why, x squared, x to the 4th, all those, I chose x cubed as my red graph to get a relationship point on here. Why place x cubed? I think I saw an x cubed here. Isn't that the first term? Are you kidding? Who would think, thought that some of these functions coming up that are fairly lengthy, that first term may determine somewhat of the shape of the graph? They have some similarities together. Now we'll jot down, in this case, it's called end behavior. On the ends, the two graphs will behave the same way. Now, I'm going to write my end behavior like this. Your textbook starts out with this. Have students to consider as x is getting large, x is approaching infinity. So, guys, if you go out this way on my graph, or the red graph, red or the blue, if you take that graph this way, x get large, on the x-axis, you keep going. Of course, your cursor will keep going. Either the red or the blue, what's it doing as you still go this way? What's my red or blue graph? What's it doing? How's it behaving? Is it still going higher and higher and higher? So we say then my function, p of x, is going higher. It's approaching infinity. Okay, now I did that out on the right. Now on the left behavior, left end behavior over here, is expressed like this. As x is approaching negative infinity. In other words, we're going out this way this time. X is going in this direction on the x-axis to the left. As it goes out to the left, guys, what's my blue graph or my red graph are behaving the same way? What are they doing? Are they dropping down further and further and further? Expressed as, in this case, my function is approaching negative infinity. That's called end behavior. Now, I like the calc notation. You guys can write your end behavior when you're asked to find the end behavior. You can write like you see it on the board right now. Your textbook does. Your textbook does not show you this, though. I think they should have, but they don't. My students are put into calc. So they express this in calculus this way. They use the word limit, or they abbreviate LIM, limit, as x is approaching infinity of my function, p of x, is infinity. So that written in the red, and that written with the calc notation using the limit, are saying the same thing. As you make x get large, my function is also getting large, in this case. This one, if you want to use the calc notation, which I prefer, this can be written as limit, LIMIT abbreviated, and you're making x approach negative infinity of this function. And of course, the answer also was negative infinity here. So if you see that notation, we're saying the same thing. Okay, let me step back and look and see if I need to say anything else about this. I don't. One local max, one local min. Now, where are they precisely? Mr. Park, Arena saying no, with the students have to wait for calculus to find precisely where that point is. I would not know myself unless I went back and did a little calculus on this. Then I could find exactly where that max and min are located. Right now, we can't, and we will not ask you to do it here in this class. But there is a max here, local max, and local min, no absolute extreme points. What else should I say about this, or am I going to leave it? I should say this. I notice my graph crosses here. That was an x-intercept. It crossed here, from one side of the x-axis to the other. It crossed here, so it's crossing at all three of its x-intercepts. Also, something else to take note of. And there's the graph. Okay, guys, get accustomed to this notation here, in the blue. Same as red. Your textbook uses the red here for calc. Now, that said, I'm going to try one more here with you. If I get some help from you, I'd like to sketch one more. That looks like, yeah, sure does. Here goes. P of x equal to this. P of x equal to x to the fourth subtract x squared. That's a binomial. I'm still talking about polynomial. That's a binomial. They want us to sketch it. Now, when I ask you for the cubic over there, someone suggested I factor out an x. I think first on that cubic over there, we finish up. This one, guys, I can clean up if I factor out a what? X squared. And that's going to leave me x squared minus 1. I think the x squared minus one's the difference of squares, so factor further, you're gonna finally get this. There it is in factored form. Now I'd like to, based on what we did over there, you see the curve over there? That was for the cubic. Now let's see what the curve might look like for this one, which is x to the fourth on this one. Yeah, you guys might start doing your business, whatever you have to do before class starts. Those doors are gonna lock on us. And I won't be able to help you. Now, anyone quickly look at this one and tell me where are the x-intercepts on this one? 0, 1, and -1, that's obvious. X-intercepts. Now, this may be also my last one I'll do through sign analysis. I love sign analysis, because we talked about it before, that applies here. But this might be the last one I'll graph using sign analysis, because I've got another way to show you. Guys, out to the left, let's start sign analysis. I'm gonna do it right here on the grid. Out to the left, I'm gonna test, I'm starting in red here. I'm gonna test maybe -3. I'll come back to it. Here, I'm gonna test -1.5. In between, we'll try +1.5. And out to the right of 1, I'm gonna try 2. Let's do it right there on the grid. Plug in -3, guys, where my placement is -3, that -3, right here. In that factored form. -3 squared, I know it's a +9, so we're gonna start with a positive. -3 subtract 1, that's a negative, -4. -3 plus 1, that's a negative, -2. All together, I think it's a positive. Is it? Oh, I didn't make a mistake. So it tells me what? The graph out here is what, above? It's above, and the guy will make a little curve to it, not a straight line. That's above the x-axis out there, through sign analysis. Next test number is -1/2, no problem. Squared, it's positive, that's squeeze that in right here, guys. -1/2 subtract 1 is negative. I'll squeeze in right there. -1/2 plus 1 gives me a positive. I'll squeeze that in there. So those three there, testing -1/2 if I have no mistake. Guys, I think altogether that's negative. Which tells me what? The piece of the graph next is where? Below. Now how far below? I don't know. Mr. Park may know. It's gotta come back. There's a low point there somewhere. Next, I'm testing between 0 and 1. I chose my test number to be 1/2. 1/2 squared. Oh boy, I'm running out of space. I put down here. Positive. 1/2 subtract 1. What's that, guys? Negative. And 1/2 plus 1 positive. Yes or no? So what does that tell me is happening with this little piece here? If I test it right, it's a negative, so that means what? It's below. It's going to drop below. Now I think, I haven't graphed it myself with a calculator, but I think it's going to look something like that. I think. I've been around long enough where this one right here may drop down lower than the previous one. We don't know. I'll make it look like that because it's cute. It's below. I'm trying a 2, put a 2 in, 2 squared is 4, I'll put that here, that's positive. 2 subtract 1, positive, +1. +3, all that's positive, which says now out here, it's going back above the x-axis. There's a graph. There's a graph of what? There's a graph of this. Right here. Now, in terms of max min, guys, we have 2 local mins, And by the way, on that last exam, a student asked me the way it's phrased, and I sort of tried to phrase it the way your textbook did. I think on my graph I had on that last exam, I asked you to name any, I think it was, name any local max or local min, I think it was. And some students just listed one. Do we actually have two here? So if they say name the local min, you gotta name both of them, okay? Aiden, I don't have this drawn precisely. They may be the same number here. That might be down -2, that might be down -2, who knows, I don't know. But it lists both of them, make sure. So guys, I have two local min. Do I have a local max? Is there a local max in here somewhere? There is, and I can name that one for sure. Is that right there? And its value is what? 0. So I know the local max for this thing definitely is 0. Then I've got two local mins. Increasing, decreasing, as you go from left to right, you can name those all day. I see intervals where it's increasing, intervals in which it's decreasing, so forth and so on. Okay, domain on this graph, no problem. Not on this one. It's open. Range on this graph. Now, I may have an issue. The range, the up and down. What might that issue be on this particular graph?
We need to look on the.
Do I know how far down this thing drops? No. Am I going to show you how to find precisely? I wish I could, but I don't want to give the calculus material out early. There's a way to find it. Okay, so I would not ask you to raise it. I'm going like this. Mr. Park, guys, do me a favor while I'm finishing up. Would you go ahead with your beautiful calc knowledge and find the local min values for x to the 4th, subtract x squared. Just tell us a little bit later on when you find them. They may be the same values. May have two of them there. Okay, but we've got two of those. Now, what I'd like to do, I added another graph here for a reason on this one. I'm going to add one here for a reason. And therefore, I think we'll cut down on the sign analysis for us after I do this. Can anyone tell me what might be the graph that you might add to this grid for a reason? Like an x to the 4th, the first term, I think over here was an x cubed. So add x to the 4th. Now, does anyone know? I don't think even that handout with the parent graphs I showed you, I don't think they showed you an x to the 4th. Does anyone have an idea what x to the 4th might look like, its shape? And I'll place it on you. Yes, go for it. Much like a parabola. Not identified as a parabola, but much like a parabola. Okay? Here goes. Just a rough sketch. We'll put this in a different color so we can see it. And we'll place, guys, here goes. She is correct. Down like that, up like that. Is that roughly a graph of x to the 4th? Now she says it reminds her of x squared. It reminds me of x squared. But it's not quite a parabola. But does it somewhat take that shape? Okay, so it may go out this a little further. In fact, I think it gets really close to the x-axis. It sweeps up like that. And over here it gets close to the x-axis and sweeps up like that. Something like that. Not a true parabola though. That's not an x squared. It's something like that. You got to block points together. Now, I'd like to know the end behavior on this one. Is my red graph and that x to the 4th graph labeled? Is my red graph and the x to the 4th graph, are they behaving the same way out here at the end? Are they both rising? On the other end, called end behavior, are these two again, the red and the black, behaving the same way? Fireball. Therefore, I know, I'm going to cut down on the sign analysis. I love sign analysis, but it's a little busy. Fireball. looks like when I start graphing one of these polynomials, looks like that first term gives me an idea of what the shape might be out here on the ends. They agree, whatever that first term, whatever that first term is doing, the graph of it is doing, my graph can be doing the same thing. So out here, it was doing this, both of them. Here's this. Down here on this one, it's cubic. They were doing the same thing here, same thing here on the ends. So if I know that quickly, I can just say, well, I'm just going to put the ends first in the attempt to get the graph. Professor, maybe I don't have to use sign analysis as much. Just go ahead and go to the ends and make it look like what should be the end behavior. And then go from there. Agree? Of course he does. He agrees. Absolutely. Guys, I could do more. I could graph an x to the 5th. I don't want to scare you. I could graph an x to the 6th. I could graph an x to the 10th. No. No, we've got an x cubed, x to the 4th, got an x squared, of course, parabola. I think that's the extent of what I need for you guys to look at. Mr. Park, did you find the precise local minimum?
It's -1/4.
Hang on before I find it. Geez, where's my graph here? Are we talking about this one? Yeah, these.
-1/4.
-1/4.
Yeah, it's same.
He says just drops down to a -1/4. And I had two of those, right?
But the value is same.
Oh, the value is how much?
Is same.
It's the same.
Yeah.
And you're saying the value is -1/4.
Mm-hmm.
Beautiful. Beautiful. Now let my students look and say, oh, I wish I knew that. I wish I knew that. Park is so smart. Arena is so smart. Oh, they've just seen it already. When I had them as students in math, they didn't know. Yeah, with that calc course, now they know. Of course, guys, I would never ask you to find that -1/4. Okay.
Yeah, I just had a question, like, what would happen if we try finding it, like just plugging in the x value? Like, shouldn't it also like,
What are you going to do? You're going to sit there and just replace x by random numbers?
we have like 1/2, for example.
You could. There's nothing wrong with just randomly sitting there and plugging in numbers and then trying to find out what's the lowest, or what number will give you the lowest value. That would take forever.
But maybe the average of two roots.
I see, there you go. You can start taking the average, maybe and get a little bit closer. Absolutely, you could do that. A little bit, yeah, time consuming. The guy, you could. I'm right.
You're always kind of on the same track, it's like find axis of symmetry, but we have to assume that it's a perfect parabola.
Yeah, exactly. I'd stay away from that. Any other questions, guys? Now let's try one if we can. Without going through sign analysis. I love sign analysis, but it takes a little time to test, have a test number, and a critical number, test it. Miriam, thought about you. Thought about you. Now, before I jump in, and we know end behavior now. And by the way, guys, let me go ahead and describe the end behavior before I leave this. My goodness. And then we'll try something here. End behavior, this is what we call this last graph. I will describe it like this. Here goes, guys. Limit. You start using that like MIT free gauge limit in calculus. As x is large of this function means you look at we're talking about that red graph. Okay, you look at the black one. As you go out this way forever, that's what x approaching infinity means. I stop at 1. No, you keep going. And as you keep going, of course, that black or red graph is being dragged along with you. What are they doing? The further out you go this way, what are the red and black graph doing? Are they rising further and further and further up, described as infinities? On the other end, in behavior, limit, as x is approaching negative infinity of this function, Now you're on the left. I stopped at -1, they said, no, go forever. Keep going. But drag those graphs along with you. As you drag those graphs along with you, either the black or the red, are they continually going up like that? Toward what? Infinity. Got infinity here. That's the end behavior of this one. I had the end behavior of the cubic graph over here. Miriam, here's what I thought about. We have the x-intercept marked here. Notice real carefully here. At this particular x-intercept, did my red graph of the function, did it actually cross over from one side of the x-axis to the other?
Yes.
When I got to this point though, which is an x-intercept, did my red graph cross over from one side of the x-axis to the other?
No.
No, it just touched at 0 and bounced right back. That can happen. And if I know it's going to happen in advance, that's going to save me some time in graphing these. The third x-intercept on the red graph, it did do what? Cross over again. So we had a cross point, crossover point. My graph down here, the blue graph for that cubic I did earlier, at this x-intercept, it crossed over from one side of the x-axis to the other. Just so happens at 0, this one also crossed over. This one, though at 0, did not cross over. It just touched. And then, of course, here at, what was it, 3, it crossed over again. Now, can someone be clever for me? And then we'll try a problem here. Can someone tell me what might, when I first look at my function that I'm attempting to graph, like I've done 2 examples for you guys. I think I erased the function here somewhere on this one. As I look at this, can anyone tell me what might tell you as a student? Is it going to do this at one of the x-intercepts? Is it just going to touch and bounce back? Or just touch and not cross over? Or is it going to cross over? Who has an idea of what in the original function might tell me in advance, which would be very helpful, that at those x-intercepts, without using sign analysis, professor, it's going to cross over from one side to the other, or no, professor, it's going to just touch and bounce back, something like this one did. This one had no bounce back. This one crossed over all the x-intercepts. Who has an idea? I saw some hands going up here. Miriam. Miriam.
Can I look at the factor form?
Absolutely.
Then I
Factor
look
form.
at
I want the factor form, yeah. You mean here?
Mm-hmm.
Beautiful, go for it.
So I noticed that the x is squared, as if maybe it's touching that point twice.
By the way, the x squared did give me, I guess, this x-intercept here at 0. And she said, Professor, I noticed there's an even exponent, 2, x squared. Ah, the next factor, Miriam, I don't want to take what you're saying there, I'm going to help you out though. The next factor was x subtract 1, that gave me this x-intercept.
Mm-hmm.
What was the exponent on the outside of it understood to be?
An odd exponent.
A 9, a 1. This one, this factor gave me a -1, this x-intercept, and on the outside was another 1, odd. Now give me a conclusion. Give me a conclusion. When you first observe the function, how are you going to know, Professor, it's going to cross or it's going to touch at those x-intercepts? What's a good way to know? Yes?
If the exponents are odd, then they cross. If they're even, then they
Exactly. If the exponents for those on those factors, if the exponents are odd, it's going to cross. If it's even, and the only even I see on the board here is this one that Miriam was telling me about. This one gave me this, it touched. Did not cross over. Okay, so guys, if it's odd, as he told me there, it's going to cross over. If it's even, it's going to do what? Touch, and my graph is on its way. Now we're going to try one. Beautiful. Without maybe going through all that sign analysis and all that business there. Guys, still in the same part, just different examples here. Yeah, see what I brought in here. Oh, I did, okay, here we go. Sketch this. textbooks, I'm gonna do it. They gave most of these in factored form for you, you didn't have to factor. Here's the first one. It's already factored for you. If you want to expand it out, I don't know why you would, but if you want to expand it out, go for it, but I'm gonna leave it in the factored form. They would know, what does the sketch look like for this, the way it looks right here. And let's see what it might look like. Don't tell me if you should expand this out. Is it a cubic, a quartic, a quintic? What type of a polynomial is it? Is it a quadratic? I know it's not a quadratic. I think it's a cubic. We actually multiplied out, I think the highest exponent was a 3. I'm not gonna multiply it out though, but it's a cubic. I sort of know then the sort of shape here. By the way, guys, can anyone tell me without expanding this thing out fully, put it on the side here for reference. What would be the first term in the expansion if you should multiply all that out? What's the first term? I think I'm hearing someone tell me. 2x cubed. Let's go play a part. Without fully expanding, I'm not going to multiply all that mess out, but the first term would be 2x cubed in the expansion. That plays a part like here, my first term was x to the 4th. They sort of give me an idea of what's going on here. Here, the other one, I think I erased it. We had an x cubed, I think earlier, gave me an idea of what's going on. This one has an x cubed, so that should tell me sort of what's going on the ends. This is in behavior. So guys, let's get that in behavior out of the way right now. And I don't think the calc notation is too hard here to understand. Just find the limits. As you make x get large of this function, I'd like to know what is my function doing, or what is my graph doing. Now, some students say, Professor, this really says x is approaching infinity. It does. I don't have the graph though. So what might you do? Go to this first term, and you could say, I'm going to just replace some x's, large x's, Professor. Since x is approaching infinity, you can start out with maybe 10. Put a 10 in there, 10 cubed is 1,000, you're up to 2,000 already. If you go up to 20 and put it in, it's going to get higher, I think. You replace x by 100, so you're making x get larger and larger and larger and larger. That's what infinity means. This right here, when you go back and replace x by those large numbers, this thing gets larger. Which tells me, out on that end, what's happening? What do you think my graph is doing? It's increasing, it's getting larger and larger and larger. Oh, by the way, is that what the x cubed graph did over there? The parent graph, was it rising on the right? So this is infinity. On the other end, let's find the limit as x is approaching negative infinity of this function. You say, Professor, how can I do it? Well, visualize here, my first term determines everything. Replaced by a negative number. So if I try negative 10, I know negative 10 cubed is a negative 1,000. Times 2, that's negative 2,000. Just replace it by a negative 10. Might even get more negative if I replace by negative 50. Cube it, and so forth and so on. Does it get more negative as the numbers get negative? Is that true, guys? Makes sense? You start replacing numbers? So the result might be what here? Negative infinity. Please tell me my parent graph, x cubed, was doing the same thing out on its ends. Woo! Now, can someone tell me, where are my x-intercepts? Where are my x-intercepts of this graph? Go for it.
Negative 1/2.
Hang on now. The negative 1/2 I will take, and I'll multiply it here. That's an x-intercept. Is there another one?
3, but it doesn't touch.
No, I'm not worried about that. I just remember the x-intercept. 3. Another x-intercept. Now, since I'm graphing this without sign analysis, can anyone look at this and tell me where's the y-intercept? Now, how would one find the y-intercept to begin with? You replace x by what? Zero. If I replace x by zero, I think this becomes 1, and I think this becomes a 9. So my y-intercept is up here at 9. I may not mark all this just to show this, but it's up here at 9. So I've got the x-intercepts, I've got the y-intercepts. Now, let's graph it fairly quickly. What do we know is happening on the ends? This. And on the right end, positive infinity, in my case, on this end right here, on the right. My graph should be doing what? Rising to infinity. Something like that. Out on the other end, which is approaching negative infinity, we calculated also the graph is going through negative infinity. It's dropping. So out here on this end, my negative 1/2 is the end of my graph right here at this moment, it's dropping. Is that the same way the cube graph did earlier? It's behaving just like the cube graph, and it should. Now, just without sign analysis, here we go. Whether it's going to be above the x-axis or below the x-axis, you can do it if you wish. But at negative 1/2, Miriam tells me at negative 1/2, Professor, negative 1/2 came from this factor right here that has on the outside an odd exponent, a 1. So what does that tell you at this particular point here, since it came from this? What should be happening at negative 1/2? It's got to cross over. If it's odd, it's got to cross over. Now, I'm going to adjust my graph here. It's still here. Just to make it look reasonable though. Yes, it's still doing this. But it's going to cross over. Now, it may go directly to 9, it may not, and come back, but it's got to pick up that y-intercept of 9 is there. Now, where's it headed? Well, it's got to head down to 3. It's got to pick up 3. I have no choice here, then it's going to look something like this. And by the way, when I hit 3, did it cross over the x-axis? No, it just touched there. Is that what we expected since I saw an even exponent? That should touch, and it did touch. And there's a graph in no time of this. No sign analysis used unless you want to. No tables, I didn't use any tables. It's based on what I know about cross, touch, end behavior, so forth and so on. Isn't that nice, guys? Mr. Park, Arena. So when you have these in calculus, that calc professor probably expects you to know how to shape it or graph this quickly. And then they have to ask you to do something else with it. Now I'm gonna do one little item with it before we take a break here, later on, before break time comes up. Here's one thing that they asked me. I'll probably give you points real quick. From left to right, is there an increasing interval on this red graph? As you go from left to right, is this piece right here increasing up to that point there? It's going to stop. Stationary. It's going to fall. It's going to decrease. Down to this point. Stationary. Stopped. And it's going to pick up and then rise again. Increase. So there's 2 what? Increasing, 1 decreasing interval. Is that true? Do we have a local max? Yes, there's a local max in here somewhere. You're not going to be able to find it. I don't know where it is myself. Is there a local min? I don't know where the local min is for sure. It's right here. It has a value of 0 for the local min. Make sense? We've done it? Okay. Jonathan, before the break comes up, which will be soon here, you know what I'm going to do? I'm going to place a point on some graph, maybe this one. I'll place a point maybe down here and a point here, and ask the students, class to help me find the average rate of change as you move from a point here, stay on that red graph and move. You're going to move from here to your destination over here. And everyone, right now, if I should go from the point here to your destination here, you say, Professor, from left to right? Yes. Well, you got right, Professor. The Yes. But is there a change now coming up here? Yes, you got, oh, professor. And finally, what, rise again? So are there quite a few changes taking place as you go from one point to the other? And they're going to ask you to find the average rate of change. And I think I discussed that way back, that I'll remind you on a graph coming up. Guys, how's this looking? Not too bad, is it? No. Let's try one more here. See some looks on faces, they're so happy to be with me. Tomorrow's a holiday, and here we are doing pre-calc. Oh, my goodness. Nice. Okay, guys. Let me see what my last one is. I think it's my last one. I want to point out something here. Yes, here goes. Oh, this one's beautiful. Like a sketch. This polynomial function. P of x is equal to, it's in factored form, thank goodness, for you. Nice, 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 nice. Looks like this one, if you should expand it out, guys, I think the leading term is x to the fourth. Which I think I saw earlier, how it behaved. So this one should behave the same way, out on the ends. I guess get that end behavior out of the way right now based on this. That's right. First, find the limit. X gets large of my function. So guys, if you go to x to the fourth and you start replacing numbers, I mean large numbers, and raise those numbers to the fourth power, do they get larger? Okay, so I might say altogether that limit would be positive infinity. Keep getting larger and larger and larger. Now, let's check the other end. The ends of this graph. X is approaching negative infinity. Now you're going up, replacing by a negative number. Like negative 10, raise it to the fourth. Negative 50, raise it to the fourth. Negative 100, raise it to the fourth. What type of results are coming out? Positive for sure. Are they getting larger?
Yeah.
Yes, positive infinity again. Interesting. That's the end behavior when I finally get to the grid of this graph. Go for it.
Can we shorten it even more and say like x approaches plus minus infinity, and then it's just gonna be infinity?
No, you don't say plus or minus. You don't say x approaching plus or minus, either one or the other. I'm gonna approach both. Okay. You're not saying that, are you?
No, I'm saying like, we can say that like as it approaches either negative or positive infinity, so it's gonna be.
Oh, I got you. I see what you're saying. I got you. Thank you. He said, Professor, if I see, this, you're talking about this? Yeah. Professor, is the answer always with an infinity with it? Does the answer contains an infinity, either positive or negative? Yes.
And I meant like, can we say, like, can we just shorten it, so.
No,
like, the algebra is only gonna be
yeah, no, we're not gonna shorten math. I don't know what happens when you shorten math. But I agree with the answer coming out is either positive infinity or negative. I agree with that, for sure. Okay, I just practice and we'll take a break here. Let's see what at first it looks like. And anyone? Oh, our race is here. Next minus 2. Okay. Now, can anyone quickly look at that and tell me the x-intercepts? Go for it.
-3, 2, and 5.
Thank you. So put -3 here. She's absolutely correct. I'll go ahead and label everything there in case I need it. She says, Professor, you better mark that as an x-intercept. She told me 2. I'll go out to 2. No problem. X-intercept. And she told me to go out a little further, Professor, up to 5. And that's out here. I do need the y-intercept, just some shape here. Guys, to find the y-intercept, point out what to do, just in case. You gotta find p of 0. Now we're just gonna go through and replace all this x's by 0, punch out the number. I think I get -2, 9, and I think a -5. Replace x by 0. I think all together, how much is that? 90?
90.
Whoa, so this graph goes up to, okay, I'll put it right here. Way up there, that's the y-intercept. Up at 90. Now, with all that said, let's see if we can get this graph done. Guys, on the ends, we've already determined it does this, I think. Is that true? Partial credit. Now, taking a close look, I noticed there was x-intercept, first x-intercept is -3. That came from this factor, which has what? An even exponent of 2, which means it does what there? Does not cross over, it just touches. That means it's going to bounce back. It may go higher than 90 and come back and pick it up, who knows? If I see something like that, I'm happy. Then it's gotta come down, of course, and pick up 2, and I think 2 came from this factor, which has what? A 1, which means it's gonna come down. An odd exponent is gonna cross here. Now, how far down it drops, I don't know, but we'll finally turn, come back, pick up a 5. And by the way, guys, was the exponent of this one also an odd? Which says it crosses. There's your graph in no time. That's the graph of that crazy function of p of x. Done. This one has, looks like, Jonathan, I see 1 local max and 2 local min.
Yes.
I'm not going to actually give you numbers for them, but I do see that much. 1 local max, 2 local min, increase and decrease. I see all that business going on. What else should I point out? I guess maybe, I could find average rate of change of 1 point to another later on one of these graphs. But at least we've got the graph. Make sense? All this makes sense? Now, my calc students, Mr. Park, Marina, they do it probably a little bit shorter. They probably do it a little bit quicker though, because they have some calc techniques that will get them to where they want to go a little bit faster than what we're doing. Okay. Wow. Almost at the break here. Any concern? I think a few of you guys have already had your break.
I was talking about turning points, they're not necessarily max or min, are they?
Beautiful, here we go. Your textbook does call these turning points. The point at which the graph turns. Okay, and they do identify those as the local max or local min. The turning points.
Well, x to the third isn't a max or a min, but it does have 2 turning points. So I was like, I thought at first it was just gonna be max and min, but it's not.
I know what you're doing, we're just gonna hold off on, we'll take a break though. One of the handouts that you're gonna get here today from me, there's a rule that works most of the time. If you wanna know how many turning points you have, Jonathan, I'm glad you brought this up, altogether I have 3 turning points. I've got 2 local mins and 1 local max, I've got 3 of them altogether. What was the highest exponent or the degree of this graph or function to begin with? 4. Usually the general rule is if you subtract 1 from that degree, the highest exponent, that will tell you at most how many turning points you may have. So 4 subtract 1 says at most I could have 3. I did get 3. Okay? So if you subtract 1 from the degree, that will tell you how many turning points. Here I see only 2 turning points. I've got a local max, local min, and my degree was 3. So 3 subtract 1, says you might have 2 turning points. And I did. This is a general rule there. Subtract subtract one from the degree to see how many turning points you have. Okay? Make sense? We have a quiz tonight? Okay. Because I'm anxious to get these quizzes back to you guys as you're working on your extra credit a little bit later. Guys, go ahead and take your break.